Howdy. This is our project called over network intrusion detection with machine learning. My name is Joshua,
And my name is Abel.
and for our project, dataset and cybersecurity research. The dataset contains network traffic data labeled as normal or intrusive, simulating real-world cyber attacks. And our research question is: can modern machine learning classifiers improve the detection rate of cyber intrusions?
And let's start off the code by the first few things we have is we import some libraries such as NumPy, Pandas, TensorFlows, sklearn for the machine learning and the visualizations with the bar graphs, ROC curves, confusion matrices. So we had to import all these and their methods to help us with the data sets.
And then the next section is column names, which just has the different column names from the data set. That way we can easily identify them and use it in the code. And then we're also reading in the KDD train data set and the KDD test data set.
And right after that, we print out both the train and the test data set that shows us the statistics of all the different values that are inside of the both data sets.
And then next, we're dropping the difficulty level from both the training and the test data.
And after that, we have we describe and we use the describe method and the end unique method, and that shows us a table of the different statistics of our data set. That shows us count, mean, STD, min, max, all that good stuff. And also the end unique shows us the different types of attacks that are being hosted by the data set.
And then next, we have a visualization of the distribution of attack types from the NSLKDD dataset. So if you scroll down, you can see the table with the different intrusion types.
And right after that, we use a method called value count, which returns the frequency of each of the attack types. And this is useful for identifying the class imbalances or the prevalence of the certain attack types.
And then next, we're defining unique values method, which prints out the unique values and their counts for specified columns in a given data frame. And basically what this does, it will then pick up all the categorical features that is in the columns of the data for function unique values and show the unique values along.
And this helps understand the distribution of categorical data in the data set also. And right after that, we have the classifying attack results. For here, we created a new binary column for the attack state for both the training and testing data to represent whether the attack is present or not, and it maps 0 if the label is normal and 1 if any other attack is being used. And this is used to give a sneak peek of the newly added column and how the structure of the data has changed. And these are the outputs. And the next thing is we have the data pre-processing checking. And what this does is it uses the is null and .sum method to check if there's any duplicates or anything like that. So the data isn't skewed. So it just checks if there's anything that's null. And right after that, we also have the checking for duplicates, which we have to make sure also the data isn't skewed with duplicates of same things. So we use the dot duplicate method and .sum method to see if there's any duplicates.
And then next, we're checking for handling outliers, which may cause noise in the training the data set. Basically, this will print the first shape of the data and data test data sets, which will give the number of rows and columns in each data set. And the plots give a view of the distribution, outliers, and the range of values for each feature in the data set, which is useful for identifying potential anomalies.
And right after that, we have the function change label that groups certain attack types into broader categories for easier classification. And this helps in assessing the balance of attack categories after grouping the attack types.
Yep. And following that, we have data normalization, which is the numerical columns in the data set and the standard scalar from scikit-learn. And basically, using the head function, we're going to use normalization to show data set for comparison. It helps by putting numerical features on the same scale, which becomes imperative for various machine learning models.
And these are the outputs for that. And right after that, we have the one-hot encoding. And what this does, the code does the pre-processing on the categorical columns in both the training data and data test. And it first selects the columns that protocol type, service, flag as the categorical features. And what this is a step that's highly important in the conversion of categorical variables in a format that can be used by machine learning models.
And then next, we have binary classification, which processes the label of attack in the data set, converting them to a binary format of normal or abnormal. It uses the map function to label everything as not normal or abnormal. And finally, the binary labels are one-hot encoded using PD get dummies and column labels reset to their original bin label values. So the result of the data frame is where the attack is represented as both binary, numeric, and one-hot encoded version.
And the next part is this next part of code is the pre-processing the attack labels in the testing dataset by converting them into binary categories of normal and abnormal. And similar to the training dataset, what we did before, we basically used the map, and we also used the pd.dummy. And this produces a data frame in which the attack label is both a numeric binary label and one that is hot encoded also.
And so the next bit of code is generating a bar graph to show the distribution of normal and abnormal labels in both the training and testing data sets. So this chart will give an overview of the class balance to respective data sets, helping the identification of potential class and imbalance problems.
And as you can see here, the training has more normal than abnormal, but the testing has more abnormal than normal. And next thing we have is feature extraction. And this code creates a data frame that contains only the numeric attributes from the binary class data set, bin data, along with encoder attack label intrusion. Then it calculates using the Pearson correlation between the numeric attribute and the attack label using the core method, and identifies those attributes that have a correlation between and then 0.5 with the encoded label. And this includes the pre-processed data set for the binary classification, ready for further analysis or model training.
And then the next bit processes the testing data set in bin data test the same way that it did to the training data set. It first creates a data frame by compressing the numeric attributes from the bin data test and encoded attack label intrusion. And so the numeric attributes are joined with one hot encoded categorical features and encoded to attack labels that are added. Finally, it constructs the data set by combining numeric and categorical attack labels and saves it as CSV.
And the next part we have here is we have the preparation of both the training and testing data set, which is required for model training and the subsequent evaluation. And this script begins by importing the main libraries, train test split, and SVC metrics of the sklearn, which the feature extraction involves creating variable X for the predictor set with the columns and bin data, except for the target intrusion. And in here, we have the data split into training and testing sets using 75% of the data for training, 25% for testing, and fixed random state for reproducibility.
And then the next set, we're going to define the list of classifiers, which are logistic regression, extra tree classifier, decision tree, random forest, naive Bayes, and K nearest neighbors, and support vector machines. For each classifier, the model is fitted on the data using X train and Y train. And we're going to have metrics such as accuracy, precision, recall, and F1 score.
And that's the output for that. And the next part is this code uses the voting classifier, which is the basic ensemble strategy that combines a lot of independent models to improve the performance of each individual model on making prediction. And the three classifiers used as same as before is the decision tree, random forest, and extra tree classifier. And by doing this approach, the advantages of different models can be obtained and probably better than one simple classifier.
And then the next bit of code assesses the performance of the voting classifier by computing its accuracy on the test data first using y-test and predictions. It then creates a confusion matrix showing the classification reports, including precision, recall, and F1 score. And then the labels for no attack and attack classes are personalized for both X and Y axis.
And below, we have the creation of another voting classifier, and this time is the hard voting strategy, which predicts based on the majority vote among the individual classifiers of the decision tree, random forest, and extra trees. And then it measures the performance of the second voting classifier, the ECLF2, which uses, same as before, the decision tree classifiers, random forest classifiers, and extra tree classifiers with a hard vote. And this allows for an effective review of the model's ability to differentiate both normal and abnormal network traffic. This is the output for it.
And then the next bit of code applies a series of classifiers on the test data set to see how it each performs. These include logistic regression, extra trees, decision trees, random forest, naive Bayes, K nearest neighbors, support vector machines, and the classifiers are trained on a training subset of test data that evaluated on the test subset. We're also going to include things like precision, recall, F1 score, accuracy, etc.
And this code below implements a soft voting ensemble classifier for the performance evaluation of the decision tree for random forest and extra tree classifiers, represented by the CLF1, CLF2, CLF3, respectively. And in the voting classifier, the predictions of these three classifiers are combined using the soft voting method, where the final prediction is based on the predicted probabilities from each of the classifiers. And this helps improve the accuracy of the classification by exploiting the strengths of multiple classifiers.
And next, we're going to evaluate the performance of the voting classifier. So this code will calculate the performance scores with its accuracy score. Therefore, it computes first and then prints out the accuracy as percentages. It plots a confusion matrix showing how many true positive, true negative, false negative, no attack, attack. And then it also makes sure the classification report is spit out.
And in this following code, a new voting classifier, the ECLF2, is instantiated with the three classifiers: decision tree classifier, random forest classifier, and extra tree classifier using the hard voting. And this process gives the assurance of the accuracy and effectiveness in a hard voting ensemble model.
And here, the accuracy of the hard voting classifier will be determined using an accuracy score function by comparing predictions against actual labels. The result will be printed as a percentage, and also a confusion matrix will be printed out.
Mm-hmm. And right after that, this code prepares by converting the X-train and the X-test into Panda data frame to ensure all the features are numeric. And it uses the method called apply in order to convert any values into numeric, and afterwards converting them back into NumPy arrays to train the model. And this explanation shows the contribution of each features of the model's predictions and is displayed in the notebook to help interpret how the model arrived at its decision. And the output being these for the training, and also we did the same for the testing data set also. And both looking similar, but all having different numbers.
And so the following code will show how to apply voting classifier with decision trees, random forest, and extra tree classifiers for a data set, also to explain the model's prediction using Lime. The first X train for test data and X test for test data and NumPy arrays are converted into Panda data frames to ensure the data is numeric using the functions from Pandas. And yeah.
And right after that, we read the code again for the train data and test data. And this time we're going to be making the ROC curves and decision tree visualization. And we also redid the columns with different names. And we applied those names into the data. So we have columns for the data now. And after that, we had the data analysis using the function unique values, which is designed to print unique values and their count of specific columns in the given data frame. And this provides an idea of the distribution of these categorical variables in the data set, and therefore will help subsequent pre-processing and analysis.
And so following, we're going to extract the unique values from the attack column in the train data frame by using the set function. The set function is important because it removes any duplicates and prints the statement's outputs distinct attack types as space-separated list.
And right after that, we are classifying the attack results, and this code below converts the attack columns for both the train data and test data frames into binary labels by mapping the values. And it ensures this by labeling normal to 0, meaning no attack, and every other attack to 1, meaning there is an attack. And this is a good cleanup step to prepare the data for machine learning, where the binary classification is required.
Following that, we're going to start handling outliers by using the shape attribute from the data frame, providing dimensions of the data set, which includes rows and columns, etc. And basically, with the trained shape, it'll return the instances and features that the testing the data set.
And right after that, we have the data encoding, and this is used for the one-hot encode, the categorical columns, protocol type, service, and flag in both the training and the testing data set. By setting the prefix, it generates a binary columns for each unique categories without any column name prefix, turning these into categorical values into multiple binary variables. And this step is important for the preparation of the data in a way the machine learning algorithm, which can take numerical input and provide numerical output, can use.
And so next, we're going to go into data splitting. So this code snippet will prepare feature matrices for X-train and X-test by removing the target variable columns from both training and testing datasets respectively. The train test split function will be used to divide both the datasets into training and testing, allocating 25% for testing and 75% for training.
And right after that, we have the data scaling, where this code scales the feature data of the training and testing using the robust scaler from the sklearn, and it scales the X train by using the fit transform, where it first calculates the scaling parameters, for instance, median and interquartile range from the training data, then performs the transform. And the code checks the shapes of the resulting scaled data, X train, X train test, etc., and targets the arrays Y train, Y train test, and Y train test, confirming their dimensions for further processing or modeling training.
And so next we're going to work on the train data, and we're going to do this by creating an evaluate method that evaluates the performance of the classification models. It calculates various metrics such as accuracy, sensitivity, precision, F1 score, and recalls using the sklearn library. It's also going to print out a confusion matrix for each model, and as well as a ROC curve.
And right after that, we use the grid search function to take in the object of the model ab and hyperparameter, get a grid parameter, and the train data X train and Y train respectively, for the purpose of using these hyperparameters with the best model using the grid search along with the cross validation. And the best model is then accessible through the model name variable, and you can call on this function in order to optimize the model's hyperparameters for its best performance. And right after that, the code trains a model of type logistic regression on the training data set X train and corresponding labels Y train using its fit method. And after fitting, it gives the performance of the trained model on both the training data set and the testing data set with the score method. And the results of the accuracy of the model of these data set, thus giving an indication on how well the model is generalizing the new data.
And next, we're actually going to implement the evaluate method on all of our models based on the X test train and the Y test train data sets. And yeah, we're going to see all the metrics and confusion matrix and ROCs.
It's for the logistic regression, this one. And that's the ROC curve. And right after that, we will print the overall score, which is the average of the 5 individual models, by adding five of them up and dividing it by 5. And then we use the creation of the DT by following the parameters is performed and the training of the data is carried out. And the score function returns the accuracy of the model of the train and test sets, which will provide a measure on how well the decision trees are learned and generalized. And after that, we do the same thing for the decision tree classifier, where we create a confusion matrices and also print out the accuracy, sensitivity, precision, F1 score, and recall score, and also print out the ROC curve using the evaluate function that we created above.
And then next, we're going to make a tree that plots and fills a color where each node and its decisions are represented as a visual manner. This will help us understand the decision tree classifier. Makes decisions based on certain input features and provides insights into the model interoperability.
And during the execution, the hyperparameter of the max depth is tuned in for the RF ranging from 1 to 11. And in the code below, the parameter dictionary defines a range of the max depth parameter, which is provided as input for grid search function, along with the RF model and data. And in this way, it is possible to decide the most effective parameter for the random forest and thus maximizing its performance.
And then next, we're going to output the evaluation metrics for the random forest classifier with all the metrics, confusion matrix, and ROC curve. And then finally, we're going to go over a K nearest neighbors classifier training on the trained data set. The model will be evaluated on both data sets and use the score method. The evaluate function will be subsequently evaluates the performance of the KNN classifier test data set.
And this also prints out all the accuracy, sensitivity, precision, F1 score, and recall, also printing out confusion matrices and also an ROC curve. And right after that, we create a create a random forest.pkl, which basically saves all the graphs and everything that we created into a separate file. And this is our project. Thank you.
Thank you.